Hello and welcome to By Excellence Tutorials. And in this video, we are going to look at velocity, position, velocity, and acceleration as a function of time. That is a continuation on what we started. We started looking at vibrations and waves. So now, before we begin to do what I want us to do today, I would want us to solve the three questions that I gave out in the previous session. The previous session after the tutoring, I gave these three questions so that you can solve. So I believe you solved, so I want us to solve them together before we proceed. So the first question was a 500-gram block is released from rest and slides down a frictionless track that begins 2 meters above the horizontal. At the bottom of the track, where the surface is horizontal, the block strikes and sticks to a light spring with a spring constant of 20 Newton per meter. Find the maximum distance the spring is compressed. Okay, so I've tried to illustrate where I have this situation and this height is 2 meters as we've been taught. And then we have a spring here, a light spring. And then we have our block and it's sliding from rest. So we know that this block is going to have the weight there. Okay, so it's sliding from rest, meaning the initial speed is 0. So this block at this stage here, it's only having the gravitational potential. Okay, it's energy, it's just having the gravitational potential energy. And then at this bottom here, what is it going to have in the initial state? It's going to have the elastic potential energy at the end of the track, which is where the spring is. Okay, so what we have is we're going to use the conservation of mechanical energy. Okay, so initial should equal to the final. If we assume, okay, we've been told already that it's frictionless. So if it's frictionless, we know that the conservation of mechanical energy is the initial mechanical energy should equal to the final mechanical energy. Now, in the initial, the energy that we have here is only, okay, the energy that we have in the initial state, we only have the gravitational potential energy, which is given by mass times gravitational acceleration times height. Okay, and then kinetic energy is 0 because the initial speed is 0. It's coming from rest. And also the elastic potential energy here in the initial state is 0 because the distance, okay, the change in displacement is not yet there. It's 0. Okay, so now the final what we're going to have is the elastic potential energy, which is given by half kx squared. So k is the spring constant and x is the maximum displacement that we're looking for here. So now if we play with this, and at the end here, it's not going to have even the velocity because it's going to come to rest. It strikes and sticks to the spring. So the final velocity is also 0. So no kinetic energy there. So what we're going to have when we play with this equation, we're going to have that, of which we can say x, which happens to be maximum, is equal to 2mg h over k. Okay, so x maximum is equal to 2, and the mass is 500 grams. So we convert the mass to kilogram, of which is going to be 0.5 kilogram. Okay, so this is, oh sorry, this is just 2. Okay, and then we multiply by the gravitational acceleration, 9.81 meter per square second. And then we multiply by the height, which is 2 meters. And we divide by the spring constant we've been given in the question. Start. So the distance the spring is compressed is going to be so it's going to be 0.99 meters. So this is going to be the distance that the spring is going to be compressed. And second, okay, so a spring-loaded gun fires a 0.1 kilogram pack along a tabletop. The pack slides up a caved ramp and flies straight up into the air. If the spring is displaced 12 centimeters from equilibrium and the spring constant is 875 Newton per meter, how high does the pack rise, neglecting friction? Okay, so if we neglect friction here, what we're going to have is that we're going to, in the initial stage, we're going to have the elastic potential energy. Okay, so when we have the elastic potential energy, kinetic energy is not going to be there, because this, in the first place, the system is okay. So in the first place, we don't have velocity. We don't have initial velocity. So we're not going to have kinetic energy, and we're not going to have potential energy in the initial state. The only thing that we have in the initial state is the spring. They are being displaced. So we have the elastic potential energy, which is given by half kx squared. And then after being, what happens? Okay, so it flies straight up in the air. So when it flies straight up in the air, it's going to have, at the maximum height, it's going to have the potential energy, okay, where the kinetic energy or the speed is going to be equal to 0. The maximum speed is going to be equal to 0, and all the energy is going to be converted to gravitational potential energy. So we're going to have that. So we're looking for what height is here. Okay, we are trying to find the height here. So what we have is a spring constant, is that, and then we also have the spring is displaced 12 centimeters. So we have to convert this 12 centimeter to meters. So it's going to be 0.12 meters. Okay, and then this is squared. And then we have the mass is 0.1 kilogram. Okay. So we have the gravitational acceleration, and we have our height that we are looking for. So when we punch on the calculator, we're going to have the left side, we're going to have 6.3. 6.3. And what would be the SI unity for this one? We're going to have Newton, okay, Newton meter, okay, because here we have a square. And then here we are going to have, we're going to have 0.981, okay, and the SI unit here we have kg meter per second squared, which is basically Newton, and we have our h. So we divide throughout by 0.981 Newton, and what we are going to have here is so the height, it's going to be 6.32 meters. So this is going to be the height. So this is how we solve our question A. And then we go quickly to question B, which says if instead it only rises to a height of 5 meters because of friction, what is the exchange? What is the change in mechanical energy? So when we have another force that is introduced, like in this case, the friction force, what we know is that we're going to use the work energy theorem. Okay, the work energy theorem is to calculate what we want to calculate. Why? Because we know that friction has been introduced, so work has to be done to overcome this friction force that is there. So work energy theorem states that the work done by non-conservative forces, of course, is equal to the change in energy or in mechanical energy. So what we have is work done by non-conservative force is given by the final minus the initial energy. So my space is not okay. What we have, okay, so what we can do easily is that we know the only energies that are here is the potential from A. Okay, we're just starting from A. So from A, what we have is only the gravitational potential energy and the elastic potential energy. These are the only energies that are on this system. So for us to calculate what we want, we know that this potential gravitational potential energy is the final energy. So we're going to have mgh minus, and the initial energy, the only initial energy that we have, the energy that we have in the initial state is the elastic potential energy. So we just have minus kx squared. Okay, so the change in mechanical energy is going to be actually the work done by this friction force. So what we have is 0.1 kg, and then we have the gravitational acceleration, and then we've been given to say the height is 5 meters. Okay, and then we subtract 875, and displacement is still the same, which is 0.12 meter squared. So the change is going to be so here we have 4.905 minus So we have 6.3. So what we're going to have here is actually negative 1.395 joules. So this is going to be actually the energy, the change in mechanical energy. Okay, so we go to the last question so that we may proceed to what we want to do today. Yeah, so the third question is, well, is similar to the first one that we did in terms of the diagrams. The figures is similar because it's starting from a certain height and going down, and at the far end you have a spring. Okay, so now, wow, even the scenario is the same. We are going to have the gravitational potential energy because it starts from rest and the velocity is 0, and also the initial. So what we have here is the conservation of mechanical energy. So we have kinetic energy plus potential energy. This is gravitational plus elastic potential energy. Initial should give us the final. Okay. Final. So in the initial stage, we don't have kinetic energy. We don't have elastic potential energy. The only energy that we have is the gravitational potential energy. And in the final state, again, we only have the elastic potential energy, because distance, which is height, becomes 0 with reference to the horizontal. Okay, becomes 0, so we're not going to have this. And at the far end, it's going to stop. Okay, it's going to rest again. So the velocity, the final velocity, is also 0, so we don't have that. So what we have here, we only have the gravitational potential energy and elastic potential energy. So what we have, we've been given we have been given the weight. Okay, so we've been given the weight, and we know that weight is actually mass times gravitational acceleration. So the whole of this is weight. Okay, so we have 13,000 Newton. Okay, and then the height is actually 10 meters, equal to half, and our spring constant is 1/10 to the power 6 Newton per meter. And then we are looking for this guy, which is maximum distance the spring is compressed. Okay, so when we punch all this, we're going to get, so we're going to get okay, so here we're going to get 260,000 Newton meter. Then we divide by the spring constant. So I've already multiplied these two with the left side, okay, and should give us x squared, so that x is going to be equal to the root of Newton meter. And what we get is 0.51 meters. So this is the distance. Okay, this is the distance of which the spring gets compressed. So we get to solve B, which says calculate the maximum acceleration of the car after contact with the spring, assuming no friction losses. Okay, so here what we have now to remember is to recall Newton's second law of motion. Okay, so we have Newton's law, which will equal to the restoring force. Okay, so this force will equal the restoring force, and the restoring force we know that is given by negative kx. So if this equals, we have ma being equal to kx. Okay, so what we're going to have is simplifying this equation. It's going to be kx over m. Okay, so if you can see, we've been given the weight there and not mass. So we can either use the equation weight is got mass times gravitational acceleration and calculate for mass and put it here. Or for you to have a precise answer, you can use the same weight that we've been given. So how do we use the same weight? It's just to introduce the gravitational acceleration both on top, on the numerator, as a numerator and denominator. So we have negative kxg over mg. So this is actually 1 because g and g can cancel. So that we have acceleration being equal to, we have 1 by 10 to the power 6 Newton per meter as our spring constant, and then we have displacement we've just found to be 0.51 meters. Okay, and then gravitational acceleration 9.81 meter per square second. Okay, and then we divide by the weight, which is 13,000 Newton. So what will be our acceleration? So acceleration is going to be, so this acceleration is going to be negative 38 for 1.9 meter per square second. Okay. So this is what we are going to have. And then C, we are asked to calculate. We are told if the spring is compressed by only 0.3 meter, find the energy loss through friction. So friction has been introduced here. Okay, has been introduced, and then we know that we are going to use the work energy theorem here to calculate the energy loss, because the energy loss will be actually equal to the work done by friction on the system. So work done, and we have to remember again the energies that are on this system, and the final energy is actually the elastic potential energy. If you have been following from the first question that we answered, the only energy that we have as the final was elastic potential energy, and should be minus the gravitational potential energy. That was the only energy that we have in the initial state. So we have K is 1 by 10 to the power 6 Newton per meter, and the so it's compressed only 0.3, so squared, then minus the mass. So the mass and this is actually the weight, so we have minus 13,000 Newton times height, which is 10 meters. So what we're going to have here now is so we have 45,000 minus 130,000. Okay, so this is joules, of course. So we have minus 85,000 joules. So this is the energy that is lost through friction. Okay, so now we have solved the 3 questions that were given in the previous session. So now we can look now at what I wanted us to look at, of which is basically looking at the position, the velocity, and acceleration as a function of time. Okay, so what we have, so we have this reference circle that we call reference circle, because when you are talking of simple harmonic motion, you have to incorporate simple harmonic motion or relate simple harmonic motion to circular motion as well. So we have this as our reference circle. So if an object or particle is moving, or a vibration from this point here, where theta is equal to 0, moves off from point Q to point P here, it's going to move an angle theta, and we can have this maybe as our arc. It's going to be the arc actually. Yeah, it's going to be the arc, which is going to be S there. So it's going to move the displacement, okay, the displacement theta. So now we have this radius here, we have it as our A, which is going to be our amplitude, is going to be the amplitude. So this amplitude, or the radius, is constant, it's the same throughout. Okay, it's not changing, it's the same. So it's our amplitude. So now, from this, we can use trigonometry to come up with what x is. Okay, the x from point O here at the center of the circle to somewhere there, Q. Okay, what is this x? So we can see that we have the, we have the sine theta, and then we have the amplitude, we can use cos. So here for x, we are going to use cos, because we know that it's going to be a cos theta. Okay, so it's going to be a cos theta. So now what you have to understand here is that this theta, which is the angle, is changing with respect to time. Okay, this angle theta is changing with respect to time. So if theta is changing with respect to time, remember what we did under circular motion. we looked at something to say that angular velocity is actually the change with respect to time. So this is actually the angular speed, the angular displacement. Okay. Oh, the angular velocity, of course. This is the. So this means that we can write theta in terms of angular speed. And then what you have to also note is that this speed as maybe a particle or an object, as it will be moving from this point at this point to P, is going to have the constant angular speed. So the angular speed is actually constant as it is moving that direction, is constant. So this equation can be written as cos t. Okay, so this is actually the angular speed. So this is going to be the equation for our displacement or the position. Okay, so the position as a function of time is given by this equation. So we are going to derive also for velocity. So now we know that velocity is actually the change in position with respect to time. That's velocity. So it's just differentiating position with respect to time. So we're going to have our position as that, and then we say, so we're here differentiating this with respect to time. So what we get? So what we get here is that once the derivative of cos is actually negative sign. Okay, the derivative of cos is negative sign, and then once we differentiate time there, what we're going to have is the angular speed. So we're going to have negative angular speed sine theta. Right? So if you are lost, you can visit calculus and see how to differentiate. Okay, so this is a trigonometric function. So you get the derivative. Okay. So this is going to be our velocity. Okay. So we can even note from here to say the maximum velocity, because sometimes you can be asked to say what is the maximum velocity. So the maximum velocity is basically that. That's our maximum velocity. So now we can get the acceleration as well by differentiating velocity. If you differentiate velocity with respect to time, what you get is the acceleration. And so if we differentiate, velocity here, what we're going to get is negative, and then we already have the angular speed. So with one, it's going to be squared cos 10. Okay, so the magnitude of the maximum acceleration is actually that. So this is the maximum acceleration, and this is, so we have to note also is that the maximum acceleration occurs when the at negative A. So when the amplitude is on the other side, or when the oscillation, because the oscillation, you have to note also that it's between positive amplitude and negative amplitude. So velocity or maximum velocity occurs when x is equal to 0, at x is equal to 0, or when this system comes into equilibrium. That's when you get the maximum velocity. And the maximum acceleration, you get maximum acceleration when you have at negative amplitude, negative A. That's when you get the maximum acceleration. So these are the equations that you have to know. Okay, so these are more like standard equations. So if you are given an equation, a position equation, you have to know that this part represents the amplitude, this part represents the time, and this part represents also the angular frequency. Okay, so we can try to solve one question. If the object spring system is described by, okay, so we have this equation, we cos 0.5. Okay, find the amplitude, the angular frequency, the frequency, and the period. Okay, so we start with A, and we are told to find the amplitude. So the first thing is this is the position. Okay, this is the position equation that we've been given. So you write the standard, you know, that is given, excuse me, is given by cos angular t, angular frequency t. Okay, so you can see that if you let these two equations, you are going to have amplitude being equal to 0.33. So your amplitude is actually 0.33 meters. So you don't need even to calculate. So you're just speaking here. Okay, and then we've been asked to find the angular frequency. Okay, so you can find the angular frequency. How do we find the angular frequency? So the angular frequency, according to this equation, is here immediately after a cos. So we have angular frequency being equal to 1.5. Okay. It's equal to 1.5, which is per second. Okay, and then we are asked to find the frequency. So we can use this first relation here, where we have the angular frequency being related to the frequency by that equation, 2 pi frequency. So we have 1.5, okay, divide by 2 pi should give us frequency. So frequency in this case is going to be 0.24, okay, per second. So this is going to be our frequency is going to be 0.24 per second. Okay, and the period. Okay, so we want to find the period, and we know that the period and frequency are inverse of each other. So we have period being equal to 1 over frequency. So we have actually 1 of 0.24. So what we're going to have is period being equal to 4.19 seconds. So the period is going to be 4.19 seconds. Okay, so that's about as simple as that. And then B, we are told to find the magnitude of velocity and acceleration, and C, the position, velocity and acceleration when t equal to 0.25. Okay, so the maximum magnitude of velocity and acceleration, we said that as we're deriving some few minutes ago or seconds ago, we're deriving for velocity and acceleration, and we said the maximum velocity is given by angular frequency multiplying by the amplitude. So angular frequency is 0.33 meters, and the angular frequency is 1.5 per second. So the maximum magnitude of velocity is 0.495 meter per second. And then for acceleration maximum, it was times angular frequency squared. So what we're going to have is 0.33 multiplying by angular frequency, this is meter squared. So what do we have? So what we have is 0.743 meter per square second. Okay, so this is the maximum magnitude of velocity and acceleration. And C, we are asked to find the position. How do we get the position now when time equal to 0.25? So nothing new here. We have already the equation for position, so it's just to substitute wherever there is time, we substitute with it, this time, which is 0.25. So we're going to have our position at 0.33 meters cos 1.5 times 0.25 seconds. Okay, and this is also in per second. This is angular speed. So what we're going to have now is 0.25 we get the position at 0.25 is actually 0.33 meters. Okay, that's the position. And then we go to velocity. Velocity, we differentiate, we know that we differentiate position, and once we differentiate, we get negative, negative amplitude angular sign. This is what we get when we differentiate. So we have amplitude, so we have negative amplitude 0.33 meters. Okay, and then we multiply by 1.5. Okay, and then sine 1.5 times 0.25. What we get? Okay, so we get negative 3.24 by 10 to the power negative 3 meter per second. So this is going to be our velocity at that time. And our acceleration is going to be, we know that when we differentiate velocity, we get this as our acceleration. So our amplitude is 0.33 multiplying by 1.5 squared cos 1.5 times 0.25. Okay, so what we're going to get is okay. So what we have is 0.743 meter per square second. And this is going to be the acceleration at 0.25 seconds. Okay, so you just follow what you've been given and then you relate. After relating, you differentiate. If you need to differentiate, if you need to integrate, you integrate, and then you get what you want to get. Okay. We now look at motion of a pendulum. I think in the first session we mentioned that under this vibration, okay, we were going to touch also pendulum, motion of a pendulum, and here we're going to see if it obeys simple harmonic motion or if it does simple harmonic motion. Now we have a pendulum. Okay, so we have a mass M here, okay, and the angle theta, and we have the length of the string. So this pendulum is swinging, okay? The pendulum is swinging. So now what we have, I'm trying to look at the forces. So we have the tension force here. And then we look at, we're going to have the weight right here. Going to have the weight. Okay, so I can just write mg. So we're going to have the weight of the bulb, mg, and then remembering that this is there is an angle here. Okay, this angle is here, which gives us the components of this weight, and here it's going to be mg cos theta. And in the x, in this direction we have, which is also here, we have mg sine theta. Okay, so those are the forces that we have. So if this bulb is displacing the distance x here, what we're going to have as the restoring force, what is going to be the restoring force? Because we know that simple harmonic motion must have a restoring force of negative kx. So you can see we talked about the restoring force to say the restoring force is always opposite the displacement. So that's where this negative is coming from. It's always opposite the displacement. So if the displacement is taking place in the right direction, the restoring force will be in the left direction. That will be the direction of the restoring force. Okay, so now what we're going to have here now as the restoring force, as this bulb is displacing, is going to be negative mg sine theta. Okay. But now you're going to see that these two equations are kind of different. The two equations are kind of different. So now, what we do now, or what are the conditions that this pendulum exhibits simple harmonic motion? So we have this bulb displacing this distance x, and we have the length of the string, which is L here. So when the angle is very small, okay, when the angle is very small, sine theta is equivalent to theta. So if the angle is very, very small, what we have is sine theta being equivalent to theta. So we say sine theta from this diagram, just this diagram, okay, is going to be x over L, like that. So if sine theta, if theta is very, very small, it's going to be equivalent to theta. So we have, so we have theta being equal to x over L, like that. So what we're going to have is, in this equation, we're going to have negative mg theta, okay? Theta is very, very small. So this theta we've also related to be x over L. So we have negative mg x over L. Okay, so restoring force is going to be mg over L x. Okay, so we can see now that from this equation, standard equation, and this equation, we can relate them, we can equate these two equations. So you're going to see that when you're dealing with motion of a pendulum, the spring constant here is equivalent to mg over L. Okay, mg over L, that is equivalent to the spring constant. And the pendulum only exhibit, is going only to exhibit a simple harmonic motion if the angle is small. So if you have a small angle, it's going to exhibit simple harmonic motion. The pendulum is going to exhibit simple harmonic motion. We looked at the angular frequency. Angular frequency, we did find to be 2 pi frequency, which was equal to root of k over m. Done. So now we've related here, and the motion of a pendulum, that k is actually equal to mg over L. So the angular frequency on a pendulum, simple pendulum, of course, is actually k, which is mg over L over m, is equal to g over L, root of g over L. So on the simple pendulum, the mass does not matter here. You can see that we only have the gravitational acceleration, and we have the length of the string or rope that is used. So the mass doesn't matter. So we can even also find for period. Okay, you can find for period. So we have period being equal to pi m over k. So it's just to substitute 2 pi m over k, which is mg over l. So we can see that m and m goes, and our period is going to be L over G. So this is going to be our period. So this is the period that you use to get to, this is the equation of period that you use to calculate on motion of a pendulum. Okay, so we can try even to solve one question on motion of a pendulum using a small pendulum of length 0.171 meter. A geologist counts 72 complete swings in a time of 60 seconds. What is the value of G in this location? So what do we have? So what we have is the length 0.171 meters. We have also the number of complete swings 72, and time we have 60 seconds. So what is the value of G? So we know that T, which is period, is 2 pi L over G, like that. Okay, so we can introduce a square both sides, where we have squared L over G, or G being equal to 4 pi squared L over T squared. Okay, so this is how we're going to get the gravitational acceleration. Now, what is our T? So our period here is actually time divided by number of complete swings, which is 60 seconds over 72, and our period is going to be 0.8333 seconds. Okay, so we can substitute these values in this equation. So we have 4 pi squared, we're multiplying by 0.171 meters, and then we divide by the period 0.83333 squared. This is second. Okay, so I do this, yeah, 3. So our gravitational acceleration is actually going to be 9.72 meter per square second. And we have calculated the gravitational acceleration. Okay, so this is how we get to calculate gravitational acceleration on a motion of a pendulum. Okay, so we've come to the end of our session, and if you found this session to be helpful, if you have not yet subscribed to the channel, kindly subscribe to the channel and make sure you don't forget to hit on the notification bell so that you get notified each time a new video is uploaded. Thank you for watching.